Assignment 146, start with a weak acid that forms an equilibrium. I'm drawing this as a structure. Equilibrium means reversible reaction. Here's the conjugate base of the original formic acid. That's where you start. Now we can do mathematics regarding this system. First question says, at the moment formic acid enters the solution, there will be 0 H plus an HCOOH. So there will be only this because it has not yet had a chance to dissociate. Cannot be in equilibrium because no reverse reaction is possible. This is very much like what Miss Holtz showed you when she had one beaker, the reactant beaker, that was fairly full, and the product beaker was empty. And so there wasn't any reverse reaction possible at that point. Now B is very simple math. If we have 500 of each of these ions, it's saying prove that the number of formic acid molecules must be 49,500. So this is simple math. We started with 50,000. And some of them dissociated. How many dissociated? 500. So that leaves 49,500 still in the associated state. C is where we start doing some interesting mathematics. So here are some probabilities. It's saying, imagine that 40% of the ions will bond together each second. This should remind you of the equilibrium island, where we had a percentage of the singles would get married each day. So going back to the chemical equation, this is saying 40% of these ions will bond together each second, compared to only 2% of the associated molecules will break up or dissociate each second. So these percentages will determine the equilibrium in this system. Alright, so it says based on these percentages, complete the sentences below to show that this example here with 49,500 HCOOH molecules and 500 dissociated, that would be the H plus and HCOO minus, is not in equilibrium. So with 500 dissociated ions, how many will associate each second? 40% probability of association. So mathematically I'm taking 0.40, which is 40%, times 500, which is the number of single ions of each kind, and that gets me 200, which is the number that goes in this blank here, 200. So of the 500 dissociated, 200 will associate each second. The second one, only a 2% probability of dissociation. 2% probability. So here I'm taking 0.02 times 49,500. And that turns out to be 990. You should verify this on your calculator. I'm hoping you've already done it. It's important that you know how to do the math, not just that you can copy my math. Alright, so now this is saying, is this equilibrium? No, it's not, because to be in equilibrium, we would need equal numbers here. For every molecule that dissociates, we'd have to have one reassociate. That's not true with these values here. D is now saying, since it is in equilibrium, it must shift. It will naturally shift, as you saw in the videos. Nature will reach an equilibrium. But how will it do that? So here's a good way to approach the problem. Not the only way, but a good way. To take a look at the two states and to link them with the two arrows, which we now can use these numbers to say how big is the arrow, how big is the arrow. So with this value here, 990 will dissociate each second. Here's my arrow for dissociation, and I can put a number on it, 990. And then how many reassociate each second? Only 200, so that'll be a relatively small arrow. So 990 dissociating, only 200 reassociating each second. So if we want to be precise, we're saying per second here. But that tells you how the equilibrium will be reached. Right now we have more molecules going to the right, fewer molecules going to the left. Therefore, the number of dissociated ions will increase. It must. The big arrow points toward the dissociated ions. So number 1 is the correct choice. In words, you could say ions are formed faster than they are consumed. So this is like having more births than deaths, or more marriages than divorces. The number of ions must increase if they're being formed faster than they are consumed. So E is saying do a similar analysis, but now the numbers are changed. You can see there are a larger number of ions. Perhaps this is now in equilibrium. So that's one of your choices. It is in equilibrium, or maybe it has too many ions now, or maybe it doesn't have enough, maybe it still has too many of the associated molecules. So try to approach this the same way and see if you can determine the numbers before I show you. One of these arrows might be bigger than the other, or maybe they are indeed the same size. Mathematics can tell you that. It does say we are assuming the same percentages. So a 2% dissociation probability, 40% reassociation probability. With those values, you should be able to calculate how many are going this way, how many are going that way. Here's my analysis. I have 2,500 per second dissociating, and I have 4,000 per second reassociating. So in fact, this is not a good representation. This arrow on the bottom needs to be big. To represent the faster rate of reassociation. So the correct answer choice here is number 2. Too many dissociated ions, you can see it. There's a big pressure going back to the left, and therefore this number, the number of these ions, will diminish as it reaches equilibrium. In words, I can say reverse reaction rate or reassociation rate is too fast to be equilibrium. But this is this kind of explains how Le Chatelier's principle works. If there are too many ions, their rate that destroys them is fast, and therefore naturally their numbers diminish. That's really how Le Chatelier's principle mechanistically functions. Final question on the page. We have 5,000 ions, which does allow you to calculate the rate at which they associate, because it's a 40% probability of association. So we can say with certainty that this is 2,000 per second. If there were no dissociation occurring, you can see these would be gone in 2.5 seconds. In 2.5 seconds, boom, 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 they all turned into HCOOH. But if we are at equilibrium, that means that simultaneously with the reassociation, we're getting dissociation to replenish these ions. And so we're really just looking for what number goes here. How many HCOOH molecules? How many HCOOH molecules will be needed to produce 2,000 dissociations per second? Since it's 2% of the total, this has to be 100,000 of them to produce 2,000 dissociations per second, which balances out the 2,000 associations per second. That's equilibrium.